Okay, in chapter 7, we're going to start talking about another way to analyze problems, and that'll be through energy analysis. So we'll talk about work and energy in chapter 7 here. So the goals for chapter 7 are we're going to overview energy, we'll define work as it's defined in physics, and then we'll relate work to both our kinetic and potential energies. We're going to talk about conservation of energy quite a bit. That's sort of the one of the fundamental things of this chapter. And then we'll also include time and how work relates to power. So we'll cover chapters 7.1 through 7.3, and then also 7.5 through 7.8. So no, won't cover chapter or section 7.4. So if we were to consider just a spring with some object on top, so like we have here, there's we have this compressed spring right here, and then this rubber ducky on top here. If we wanted to find out how high this rubber ducky would go, we would need to figure out. We could use the kinematic equations, but we would need some acceleration, right? We need to figure out what the acceleration upwards is, and that way we could find its velocity and all that stuff. But we can get this acceleration from Hooke's law, this F equals negative kx, and also Newton's second law, that F equals ma. So negative kx, or the spring constant times the distance that's compressed, is going to equal the mass times acceleration, the mass of the rubber ducky times the acceleration of the rubber ducky, right? We have F equals ma. But if we change x, then the force is different, right? So as x becomes less and less, it's becoming decompressed, and so the acceleration is actually becoming less because the force on it is becoming less. So if we look at a second figure here, so we started out with it being very compressed and it's less compressed now. There's actually less of a force acting on the rubber ducky, right? Because the compression is less, right? So I had some larger force here, spring constant times the x that is compressed. Say it was maybe this is the uncompressed height up here. It's compressed all the way down here, so it has a greater force than it would from here down to here, right? So we actually have less force there, which is going to cause a different acceleration at this point than it did at this point. And then here we'd have even less compression here, so the acceleration would be less. And here, maybe this is the point in which the spring is in equilibrium, and so there's no more acceleration. So we had a large force given a large acceleration, less force with less of an acceleration, and then finally no force with no continued acceleration, right? And so obviously the rubber ducky flies up and then lands here, right? So in order to solve a problem that is complicated like this, where we have this varying force that varies with the distance the spring is compressed, or varies with time, since as it increases in time, then it's becoming less and less compressed, then we would have to do a very complicated procedure. Maybe we'd have to figure out what the force is at each point, and then take another small chunk of time and figure out what the force is there, and then figure out the force there, and a bunch of different forces giving a bunch of different accelerations, and then each acceleration has a velocity involved with it, and it gets very complicated. So we actually have, in this chapter, we'll introduce another procedure that we can use to solve this problem, and that is energy analysis. So this chapter is going to focus on that energy analysis, which is a very important unifying concept in physics. It unifies several of the different theories, and that concept is the conservation of energy. So what conservation of energy says, and this is just taken from your book, is that the total energy in an isolated system is constant no matter what happens within the system. In other words, the energy is neither created nor is it destroyed. It just goes from one form to another. And what I mean by an isolated system here is just sort of like a free body diagram, really. It's just what we're considering. We just want to look at maybe we have just a canister of some gas or something in there. If I just look at the gas inside the canister, then I would say the total amount of energy in that canister, if it's isolated, if there's no kind of heat transfer, if there's no one kicks the can or anything like that, then the total amount of energy in that can is constant. Obviously, if I had some external force, an isolated system is a system in which there are no external forces. If I had an external force, such as someone kicking the can, then the energy would change in the can, right? Somehow somebody kicked it, then some of that energy would be transferred to the walls of the canister, which would be transferred to the gas, etc., right? But if we just have an isolated system, and we'll consider most of our problems to be isolated systems, then the total energy is conserved in that system. It's similar to the conservation of mass, which you might be familiar with conservation of mass already. So if you have a chemical reaction, then two things sort of chemically react together and to form something new, or to break apart into two other things. And that you have the total mass remains the same, right? You put two things together and their masses come together and they may create one mass, but the total mass is still the same as it was when there were two separate entities. So this is pretty much, and this is of course if you don't add any more mass to it, right? So it's the isolated system. If I don't add any more mass to it, then the mass remains constant, right? So same thing with conservation of energy. If I don't add any energy to the system, then the energy remains constant. Okay, so we're just saying that the total amount of energy remains constant in a system in which we don't add any energy to it. Makes sense. Now, we have different forms of energy, though. Energy can take on many different forms, just like in a chemical reaction, the mass can take on many different forms, right? So one of the first forms here we'll talk about is kinetic energy, and this is the energy of anything that's moving. So when things are moving, we say they have kinetic energy. Potential energy is a stored energy. So that's the ability to turn into kinetic energy, or actually the ability to turn into kinetic energy or electrical or chemical or nuclear or thermal or just deformations as well. And that's potential energy is just some sort of energy that is stored up. So we have amongst potential energy, the couple we'll talk about are gravitational potential energy. This is potential energy due to gravity, right? You think about this, kinetic energy, maybe you have a ball falling, right? The speed at which it can go depends on how high it is, right? And it's actually the way it gets its energy is from gravity pulling down on it, right? And so the amount of potential energy it has is equivalent to or related to how high it is and how hard gravity is working on it. This is gravitational potential energy. I'll give you guys an equation in a little bit, but gravitational potential energy is the amount of energy that an object can do with the assistance or by gravity. We also have spring potential energy, or we call it elastic potential energy. This is, take a rubber band and stretch a rubber band apart, then that rubber band has the ability to move back towards itself, right? Or same thing with a spring. If I push on a spring, then that spring has the ability to bounce back, right? So this is the energy stored in a spring or some rubber band or anything elastic, really. It's important that we talk about this being elastic later on, that it has the ability to go back to the state it was in before it was deformed. And there's also a lot of other types of potential energy. We also have electrical energy, and chemical energy, sort of similar to that reaction that I was talking about earlier. And then there's nuclear energy, there's thermal energy, there's energy in deformations. If a piece of steel deforms, then it would take some energy to deform it, right? If you were to get in a car crash and your your car deforms, then there's some energy there. So just sort of a breakdown of how energy changes, but it's conserved all throughout here. The sun provides some energy, and it provides it in the form of sunlight, right? And then this plant right here absorbs that sunlight along with nutrients from the ground and whatnot, some energy from the ground, and it turns into a form that's usable for this guy to eat a hamburger, and then or some sort of sandwich, and then it turns into energy for him, right? So it becomes calories, right? So the sun gave energy to the plant, when the plant gave energy to the guy, and then the guy put a bunch of energy into this barbell as he was working out, right? So this is the way energy can transform from one form to another, but it's conserved the entire time. So just to give you a little bit of an example of how energy can go from one form to another, but still be conserved, is that if we have two cars that collide head on, and then both of them come to a stop, right? There was obviously some moving or kinetic energy before the collision took place, right? So we knew you could just observe that there was kinetic energy, but then they come to a stop, right? And so that energy must have gone somewhere, right? The energy had to have been conserved, so it must have changed form into somewhere else. So take a second, pause this, and ask yourself, where did the energy go after the collision? And we could say that some of it went into deformation of the cars. Like I said, deformation is a form of energy. If I'm gonna bend some steel, I have to put some energy into that steel, right? So one of them would be deformation of the cars. Some other ones might even be the sounds that are produced by the wreck. That would create some. It's actually sound is pretty much just a pressure wave, so you have to have some sort of force and some sort of energy to create that wave in order to hear it. So some of the energy has actually gone into sounds that are produced by the wreck. There's also some thermal energy that is produced during the wreck. What are some of the objects that had an increase of thermal energy? We could say, well, the cars are probably skidding on the road, right? They probably hit their brakes, and so we could say that the road had an increase of thermal energy due to friction, right? And we could also say that the cars themselves, as they bend, that metal becomes warmer, right? And so there was some thermal energy into the cars as well. So they had kinetic energy, and then it turned into a whole lot of other different forms of energy, but it was all conserved. The total amount of energy after the cars collided is actually the same amount of energy before they collided. So before we talk about energy in great detail, though, we need to talk about work. Work and energy are closely related. They actually have the same units. But formally, the way that work is defined in physics is that we have a force, some force F here, and we have some displacement, which we'll call S. Both of these are vector quantities. And the work done is the amount of force through a displacement S, or the product of the force and the displacement. So the force times the displacement S. Now, the force here has to be parallel to the displacement. So work is defined as the parallel force, or the force times displacement, but that's the parallel component of the force, or the component of the force parallel to the displacement. So if force acts perfectly horizontally and displacement is also perfectly horizontally, it just becomes the force times the displacement. Now, if we were to draw a free body diagram of this, we also know that there's a weight acting down and a normal force acting upwards, right? But in order to find out what the work done, if the block moves to the right, the displacement is to the right, then I need to find my component of the weight. I'm looking for how much work gravity did on the block, or how much work was from the weight. Then I would need to find the component of the weight that is parallel to the displacement. And we know that weight is straight down, and there is no parallel component to the displacement. So the work done by gravity is actually zero, because gravity acts down, but the displacement is to the right. So there is no work done by gravity. Similarly, the normal force acts upwards, and there is no component of the normal force acting in the direction of the displacement. So the work done by the normal force is also equal to zero in this case. Now, of course, if I were to put this down an inclined plane, then I would have some component of the, and it would slide down the inclined plane, then I would have some component of the gravity, of the weight, that would act in the direction of the displacement. Then there would be work done. Or maybe easier to see is that if I take this and this force were not parallel, let's say I have a force that runs up off at some angle, maybe 45 degrees off the horizontal, then I need to find, in order to find out how much work was done by that force, I actually need to resolve it into its components. I would need to find the x component and the y component. Only the x component would then do work, because the y component is perpendicular to the displacement. Only the x component is parallel to the displacement. So work is equal to the force parallel times the displacement s. We use s for displacement. Basically, what I was just talking about here, if we have a force applied at some angle, we have to break it into its components, right? So if we have some force acting over here, somebody's pushing this car, it's acting at that angle there. The angle here is phi, and so the work done is the force parallel times the displacement. The displacement is along here. Then the parallel force is F cosine phi, right? This is this one right here. And so the work done is F cosine phi times the displacement s. So F cosine phi times s. The units for work, well, we can actually figure out what the units are. We have force is in newtons, right? And then displacement in SI units is going to be meters. And so the SI units are a Newton meter, which is also known as a joule, named after James Prescott Joule. The English units would be a foot pound. So this is our force here, and then this is our displacement. We say foot pound instead of pound feet, though. So we'll use mostly joules, however, since we'll do mostly SI units. Again, the part of the person's force that is perpendicular, this is the force perpendicular right here, will be F sine of phi, and it does absolutely no work whatsoever because, again, the force is perpendicular to the displacement. So in physics, we define that as zero work because it did not move in that direction. Now, if the car did move off in this direction a little bit, then it would have done some work. But since it didn't, it moved perfectly horizontally. There was no work done by the perpendicular component of the force. Now, work is a scalar quantity. It doesn't exactly have a direction on it, right? If I push something off to the left, if I push something off to the right, then I do the same amount of work, right? The direction doesn't really matter, so it's not a vector quantity, it's a scalar quantity. But I do have to talk about, because I have different forces at work, and this sort of plays into Newton's third law a little bit, I have to be careful about what's being worked on. If I'm pushing on a box, and there's also friction acting on the box, right? I push on it and I push off to the right, then I do some positive work on the box, right? Because I am pushing it in that direction. But there's still some work done by friction. Would I say that the work done by friction is exactly the same as the work done by me? Well, the magnitude, actually, the magnitudes would not be the same, and we wouldn't say the direction is the same either. So we have to be very careful about what object is being worked on and by what force. I said the magnitudes won't be the same. I'll talk about that in a second. But I just want to talk about sign convention at first. We call positive work here. Positive work is defined when displacement is in the same direction as the force. So if I push to the right on a box and the box moves to the right, then I have done positive work on the box because my force is to the right and the displacement is to the right. Because they're in the same direction, it's a positive work. So as long as it's the same direction, the work is positive. Friction, however, opposes motion, right? So friction works back to the left. I push on the right, friction pushes to the left, but it moves to the right. So because friction's force is to the left, but the displacement is to the right, we say that that's negative work. So the force of friction is a negative work. So basically the way I can summarize that is to say that negative work is when displacement is in the opposite direction as the force. So if something pushes to the left like friction, but it moves to the right, then it's a negative work. So a quick little question here. Pause this and you guys can answer this. If I lift a book, take a 1 Newton book, or the force I put on is 1 Newton, and I lift upwards 1 meter, what's the work that I do on the book? Well, I push on the book upward with 1 Newton, it moves upward, so that's a positive work, and the force is 1 Newton, the displacement is 1 meter, so 1 times 1 is 1, and so I have 1 joule, a positive 1 joule of work done. What's the work that gravity does on the book? Well, the work of gravity on the book would be it's moving down at 1, or gravity, if gravity acts down at 1 Newton and it moves upwards 1 meter, then I would say that the work done by gravity on the book is equal to negative 1 joule. It might be, this would have to be at a constant velocity. It would have to be a weight of 1 Newton for this to be true. But this example is strictly for just showing positive and negative here. So if gravity acts downwards at 1 Newton, yet it moves upwards at 1 meter, then it would have to be a negative 1 joule for work. So gravity acts down, but it moves up, so it's negative. So like I said, I would say something about the forces or the works not being equal. If I push on a box to the right and friction pushes back, they're not actually, if it moves to the right, they're not actually going to be the same magnitude, but there will be opposite signs. So it's not exactly like Newton's third law. But let's run through an example here and maybe bring it together a little bit more. So let's say I have some box sitting here and I push on it with a force F equal to 10 newtons. And it displaces some distance S equal to 4 meters. And let's just say this box had a mass of 10 grams or 10 kilograms, and the coefficient of kinetic friction between the box and the surface here is 0.1. We know, you guys probably want to just jump right into chapter 5 material and Newton's laws and say, oh, I have a frictional force back here and a positive force here, and then do a summation of forces and find out your net force. Well, we can do a very similar thing with net work, or we'll call it total work actually in this case. And so first we find out what's the work that F does on the block, the force F. And so that one, we don't even need to consider friction in there at all. So that's just going to be 40 joules because I have some 10 Newton force that displaces it 4 meters, and this is a perfectly horizontal force, right? So I have 10 times 4 is 40 joules. Now, what's the work that friction does on the block, little f? So in order to find that one, well, the direction that friction acts is going to oppose motion, right? And it's still opposing at a distance of 4 meters. So that distance is the same, 4 meters. And in order to find the frictional force, that's the coefficient of kinetic friction times the normal force, right? And since this is sitting on a flat surface, then the normal force is the same as the weight. So that's going to be 10 kilograms times 9.8 meters per second. So we have, if you guys run through the math, I don't have the actual computation shown on here, but we'll have mg will be 10 times 9.8 times mu k times 0.1, and then so that's mu k mg, which will give us, let's see here, 10 times 9.8 times 0.1 is, well, 9.8, right? 9.8, and then it goes over a distance of 4 meters, right? It still acts over this 4 meters, and so the total work done is going to be 39.2 joules by friction, but remember, friction is pushing back to the left and displacement is to the right, so that's a negative 39.2 joules. And then, just like we did summation of forces in chapter 5, we can do a summation of works done by the two different forces, and we'll get a total work. 40 plus negative 39.2 will give us a total of 0.8 joules. So we can find the total work by algebraically adding all the works together to get this. Or, and this is a good exercise for you to do, is go through and do the chapter 5 stuff, in which we have some force here, some force back here of friction. We can find a net force between the two, which should be 0.2 newtons net force to the right, and then that net force times that displacement will give us the total work. So 0.2 newtons net force to the right times 4 meters would give us 0.8 joules. So there's two different ways we can actually find the total work done. We can either find the work done by each one, make sure that we use the correct signs, and then we algebraically add them together, or we find the net force and then take the net force times the displacement. Two different ways we can do it, and I urge you to sit down and just run through that quick little problem, which you find the net force and multiply it by the displacement, and get the same answer we got by adding the works together. So in here we have a net force which causes some acceleration, right? So the net force causes some acceleration that you guys got from running through the example that I said, or the problem that I said. But we also have a difference in work, which also causes an acceleration. So net force causes acceleration, or a difference in work done by the two forces also causes an acceleration, which is very important concept to be able to put together. We can have a difference in work which causes some acceleration, but that also means we have a net force that gives us the same acceleration. So I can actually take my difference in work, or my change in work, and talk about the net force, or the change in acceleration, right? Difference in work will give us an acceleration, which will also relate to a net force, which we'll use very importantly for the conservation of energy principles. But think about that for a second. Difference in work causes an acceleration, okay? Or causes, or relates to a net force. So I said that before we talk about energy, we had to talk about work, right? So how does work actually relate to energy? We know now that if I were to lift a book 1 meter upwards with a force of 1 Newton, I've done some work on the book, right? And the amount of work that I've done on the book is 1 times 1, which is 1 joule, right? So I've done 1 joule of work on the book. But the work that I've done will allow gravity to also do work on the book, right? I lift it up a meter, well then gravity can pull it right back down a meter, right? So it can also, and it can do the same force if it wanted to. It could use a Newton times a meter, and it would do a joule of work, right? I would do a joule of work lifting the book up, and gravity could do a joule of work back down. So better way to say it is the book, through gravity, can now do work on me. If I let it fall in my hand, then the book will do one joule of work on me. So the work that the book can do is what we call energy. And that's actually potential energy. The amount of work that this book can do after I put work into it is the energy that it has capable, right? So work done is equal to the energy, or the work that can be done is what we call the energy. The amount of energy that the book has is equal to the work it can do, which is 1 joule, right? Which is actually, because the conservation of energy is the same amount of work that I put into it. So the units, ask yourselves, what are the units of energy, right? So we say the energy is equal to the work it can do, which is a Newton meter or a joule. So the units of energy are exactly the same as the units of work, that are joules. So they actually have the same units. They are very, very similar. Okay. The form of energy that I was just talking about in the last example was gravitational potential energy. We talked about that a little bit earlier in the video. We said that if the work is done by gravity, if the force supplying to the half of the work, the force causing the work is a gravitational force, then it's gravitational potential energy, right? I lifted the book up and it had some more height and it could fall, right? And so that was work that could be done by gravity, so we call it gravitational potential energy. Okay, that's because it's gravity that's applying the force of the work. The formula for, or the equation for gravitational potential energy, and sometimes I'll write PE, but most of the times I'm just going to write U grav, and actually I'm just going to write U as I do problems on the board in class. I'll write U for gravitational potential energy. I'll drop off the grav. But this is mgh. U grav is equal to mgh. This is, mg is the force of gravity, h is the height at which it falls. So it's actually just work. It's actually just the force times the displacement. The force happens to be, in this very specific case of gravitational potential energy, the force is mg, mass times gravity. And the distance it goes, the displacement, is the height at which it falls. So gravitational potential energy is mgh. Another type of potential energy that we have is elastic potential energy, which I told you guys earlier in the video. The equation for elastic potential energy, or potential is U, elastic, or this is what I'll usually write on the board, is just UEL for elastic potential energy, is equal to 1/2 kx squared, which comes from Hooke's law. I won't go through the derivations, but it comes from Hooke's law, in which our force is equal to negative kx, right? And then the displacement is x, right? The distance at which it goes is x, and you can see how it's related to Hooke's law. So the elastic potential energy is 1/2 times the spring constant k times the distance that the spring is either compressed or stretched. This is the distance from equilibrium here, x, and it's just 1/2 kx squared. The distance is stretched or compressed, it doesn't actually matter when we're talking about energy, though, right? If this were a negative x, then it would be some negative squared, it'd still be positive, right? Or if it's a positive x, then when it's squared, it's still positive. So the work done, or the energy potential in it, is the same regardless if it's stretched or compressed, as long as the distance is the same. So elastic potential energy, 1/2 kx squared. Now we also have energy of things in motion, right, which we called kinetic energy earlier. So think about this for a second. Take it, pause it for a second, and what quantities does kinetic energy depend on? You have something moving. When you say, well, that's a lot of energy in that thing that's moving. We would say a baseball going very fast versus someone just throwing a water balloon not nearly as fast. Which one has more energy? And hopefully you say the one that's moving faster, the baseball has more energy, right? What if I say I have a car going 50 miles an hour. Maybe the baseball is going 100 miles an hour. The car is only going 50. Which one of those has more energy? Hopefully you guys would say the car in that one. And so you say that it has some, it's dependent on the mass, right? The size of the object, the baseball versus the car, as well as the speed, the water balloon versus the baseball, right? So it depends on the mass as well as the speed. And the direction doesn't actually matter in kinetic energy, right? It doesn't matter if the car is driving forward at 10 miles an hour, backwards at 10 miles an hour. If it hits something or someone, it's going to hurt the same regardless of the speed, right? So it's actually just going to depend on the speed and not really the direction. So the equation for the kinetic energy, which is very similar to the equation for elastic potential energy, is that kinetic energy, or I'll just write K a lot of times, is equal to 1/2 mass, the mass of the object, times its velocity squared, or actually this is speed squared, since speed doesn't matter, and if you square a vector, it doesn't have a direction anymore anyway. So the kinetic energy present in something is equal to 1/2 times the mass times the speed squared. So we're moving towards talking about conservation of total energy. But before we talk about conservation of energy, we need to define what mechanical energy is. So mechanical energy is defined as the energy associated with motion. This is your kinetic energy. Position, which would be your gravitational potential energy, and deformation, which would be your elastic potential energy. The deformation that I talked about with the cars getting in a wreck earlier, and the steel bending, would actually not be mechanical energy, and I'll talk about that see why that is in a second. But it's associated with motion, position, and deformation. It doesn't include any other energy forms like heat, sound, electric fields, nuclear energy. Any of those are not included in mechanical energy. It's just essentially your kinetic, your gravitational potential energy, and your elastic potential, basically. It also doesn't include deformations that do not naturally return to their undeformed state. Right? So I said that the steel in the car accident earlier, it isn't included in mechanical energy, and that's because the steel doesn't naturally spring back, right? Once it's bent, and it stays that way. It might spring back a little bit, but it's pretty much stays that way. So it doesn't include deformations that do not naturally return to their undeformed state. So this means that it only includes deformations that return to their undeformed state, which is what we call an elastic deformation. Something that is elastic and bounces back, right? You take a rubber band, you pull it apart, you let go, and it goes back to exactly the same shape it had before you stretched it. This is an elastic deformation, something that bounces back. You take a spring, you compress it, you let go of the spring, and it bounces back to the same shape it had before. Of course, you pull a spring apart, and you pull a certain distance, it might snap back to the way it was before. If you pull it too far, though, then it's not going to return to the state it was in. We say it's past its elastic limit at that point, but that's not covered in this class. But we'll only talk about in mechanical energy deformations in which things return to their natural state. Okay, so like I said, it comes down to just kinetic energy, gravitational potential energy, and elastic potential energy. So then we can define the total mechanical energy of a system as all of these energies added together, the kinetic and the potential energies. Remembering that potential energies includes two things, gravitational as well as elastic. So we say the total energy is equal to the sum of kinetic and potentials. So all the kinetic energy plus all the potential energy equals the total mechanical energy, but I'll just say total energy since that's the only forms of energy we'll talk about in this class. So Generally, mechanical energy is just it's energy that can be readily transferred between potential and kinetic energies without any loss or any sort of transformation from one form to another, other than these potential and kinetics. Okay, so if I just like the book example I had where I lift a book up, I put some I had it had while I was going up, it had kinetic energy, and then that turned into potential energy once it stopped at the top, right? And so that was mechanical energy. Any force that turns mechanical energy into a non-mechanical energy is what we call a dissipation of mechanical energy, or the energy dissipates, right? It disappears. So some way in which, or some force that removes the mechanical energy of the system is called a dissipative force. Friction is a really good example of this. So if we were to consider a block that's moving across the floor, then we have friction would cause the velocity to slow down, right? And then the kinetic energy would decrease. It was going at some initial velocity, so it had some initial kinetic energy, and then at some time later, it has stopped and it has no more kinetic energy, right? And if it's gone along a level surface, then we haven't got any increase in our potential energy, right? There's a typo here. Sorry about the typo. This should actually say KE. So we don't have any increase in potential energy from a loss in our kinetic energy. We lost all of our kinetic energy. We had some to start with, and then it went to zero. As soon as it stopped, the kinetic energy was zero. But it didn't go up. It didn't compress against a spring, and it didn't move up in height. So we didn't get any elastic potential energy out of it, and we didn't get any gravitational potential energy out of it, right? This is because friction has dissipated the mechanical energy. Okay, so we don't, I mean, the total energy is still conserved. We actually still have the same energy in the whole system. If we were to talk about the block and the floor all together as the whole system, then we still have the same amount of energy, but we don't have the same amount of mechanical energy. We can't readily take that block after it stopped and drop it again and get the same energy out of it, right? So we still have energy is conserved, but the mechanical energy here is not conserved. It's dissipated by friction. What happened in that previous example is that before it was sliding, it's sitting here, and the molecules between the block and the surface of the surface it was sliding on, they were sitting here and they were vibrating kind of slowly, right? And there's a little bit of energy in there. There's as long as things aren't completely frozen at absolute zero, then there's always some little energy in the molecules. But that's not part of this class either. But they're moving a little bit, and then it slides, and it slides along. Friction is acting back this way. It's hitting all these little bumps that we define friction, to be this roughness between the surfaces. It hits these, and it puts some more energy into the system, and actually you have these things moving much faster. So it actually transferred heat to the surface that it was sliding on, and that heat is actually more kinetic energy in these little molecules. Basically, these molecules are drawn with little springs attached, and so they're all feeling each other. But these molecules start moving faster, and so they actually have more kinetic energy, right? So this is what's really going on. The total energy is still the same, but the mechanical energy, and this is why it says that energy can be lost as heat, is because the mechanical energy is dissipated. We had some kinetic energy along here, and then the kinetic energy disappeared. We can't get that kinetic energy back in a mechanical form because now it's in heat in the floor, and it's kind of hard to extract that energy. Okay, so mechanical energy is not conserved, it's lost due to friction, but total energy is still conserved in this case. Or actually always. So if we make the assumption, or if we have a really smooth surface, and we say that there are no dissipative forces like friction present, obviously that have to be no air friction, no air drag as well, then we can say that mechanical energy is completely conserved, right? So we can say here is that the initial kinetic energy plus the initial potential energy is equal to the final kinetic energy plus the final potential energy, right? And this initial and final can really be at any point, right? I can call this is point 1, 2, 3, 4. Let me call point 1 as my initial and point 2 as my final, right? And so I can actually say, all right, my kinetic energy plus potential energy is the same everywhere. Well, I'll assume that velocity is 0 at this point. So what's my kinetic energy at this point? Well, my kinetic energy, which I put in here, would just be 1/2 mass times velocity squared. Mass is 50, but velocity is 0. So my kinetic energy right here is 0. We'll actually work this problem out. I'll put this problem up on Lima, and you guys can check this out. We'll fill in all these blanks on here. But if I go back to this first one, then we have the kinetic energy here would be equal to 0. And then the potential energy, and actually the velocity here is 0 as well, so I can fill in both of these at the same time. Potential energy, remember, this is going to be, there's no springs. There's no springs anywhere in here, so I don't need to worry about the 1/2 kx squared. But there is gravitational potential energy, right? It's on Earth, and it can fall at some distance, right? It can fall some height of 4 meters. This is, if I call this is where h is equal to 0, then my height here is 4 meters. So it would have a gravitational potential energy of mgh. So 50 times g, which is 9.8, times 4. So I could say this is 200 times 9.8 is our potential energy here. So that is equal to 1,960 joules right here. So my total energy, which I'll just put ME, this is for mechanical energy. The total mechanical energy is, this is 1,960 here, this is 0 here. I add these up, I have 1,960 joules of total energy. Now, I can find out, given that I have a height here, I can find out how fast I'm moving at point 2 actually, just from knowing a height difference. Because I know if my mechanical energy is conserved, this is 1,960, so is this here, so is this here, so is this here. They're all 1,960. And this plus this will always equal this. So because I have a height and because I have a mass, I can find out what my potential energy is right here. So I encourage you guys to try to work out this entire thing here and find what your potential energy is. 3 times 50 times 9.8. And then this right here would just be whatever else I need to add to this to get that. Or we can just say mechanical energy minus potential energy would be our leftover kinetic energy. Then from there, since kinetic energy is 1/2 mass times velocity squared, and we have a mass, we should be able to find our velocity or our speed as well. Not so much velocity, but speed, because we can't get a direction. And then we can also do this at point 3. Well, at point 3, we have no more potential energy, right? So our kinetic energy is 1,960 joules here as well. And we can find the velocity from there. And then at point 4, we're given a speed, 6 meters per second, but we don't know the height. So this one, we have our mechanical energy. We can find our kinetic energy because we have a mass and a speed. Find the kinetic energy, and then potential energy would be mechanical energy, total mechanical energy minus the kinetic, will give us the potential energy. And since the potential energy is mgh, and we have an m, we can find out what h is right there. So I encourage you guys to work through that one, but like I said, I'll put this up on La Lima along with other problems. So that works nicely if we have a frictionless world. But what if we don't have a frictionless world, since we really don't have a frictionless world? How will we deal with friction in energy analysis? So in order to do this, you got to remember back that the energy is equal to the amount of work that an object can do, right? So I remember when I lifted up in the book, I put some work into the book, and then the energy was the amount of work that I put into it, right? So I can say that there's this theorem here, work kinetic energy theorem, or actually it's the work energy theorem, but if I talk about kinetic energy specifically, then the amount of work done is equal to its change in kinetic energy, which makes sense, right? Work and energy are one and the same, so the amount of work that is done is equal to its change in kinetic energy. So if something is moving quickly, actually, if you think back to that block that we had earlier, that had kinetic energy in the beginning and it had zero kinetic energy at the end, well, that's because the work done was equal to the friction, the frictional force times that displacement, right? So the amount of work done by friction was actually just its change in kinetic energy. So we can also say this is your final kinetic energy minus your initial kinetic energy, right? And important thing on that block example, if I have final minus initial, this would actually be 0 minus some value. So I would have actually had a negative work, right? Which friction did a negative work, right? The displacement was to the right, but friction worked to the left. So the work done by friction was negative, which actually works out to be the same sign as our change in kinetic energy, our final minus initial, okay? Or more generally, we say that the work done is our change in total energy or total mechanical energy. So the total energy final minus the initial total energy, which would encapsulate the change in gravitational potential energy and also the change in elastic potential energy, right? So obviously in gravitational potential energy, mass times gravity is the same, so it actually just comes down to a change in height, really, hf minus hi. And elastic potential energy is since k is a constant, right, and 1/2 is obviously a constant, then it's actually your change in the x squareds, right? So it's the difference of the final position squared minus the initial position squared. It's the difference of the squares between them. This is equal to 1/2 k times xf squared minus xi squared. So that's this is just always the work done. And we have to think which case is going on physically in order to know which one we're going to use. Did we have a change in how it moved in the speed? Did we have a change in kinetic energy? Did we have a change in its position? So a change in gravitational potential energy? Or was the spring compressed and elastic potential energy? And it's possible that we have more than one thing happening at once, right? We could actually have, and we will have, a spring push in on something, so we have a change in elastic potential energy, and it turns into kinetic energy, right? And we have the work done by the spring is equal to how much energy we get out of it. But we'll do some example problems for that one later. So we revisit this problem here. Let's give it some coefficients of friction now. Let's say that the kinetic coefficient of kinetic friction is 0 on the entire ride here. And then we want it to slow down, so we rough up the edges down here beyond it, and we say the coefficient of kinetic friction is 0.5 just after the end. Can we find out how quickly it would come to a stop, or how far it would go? Of course we can. We can ignore all this stuff in here. This entire loop and all these bumps don't really matter, right? Because once it gets down here, we have some work that will be done by friction. How much work is going to be done by friction? It's going to be the energy. It's going to be all the energy. When it comes to a stop, it's going to be kinetic energy here, and then it's going to become 0. So the work done by friction is going to be the entire kinetic energy here. And the entire kinetic energy here, because it's at the bottom, it's actually the same as the kinetic energy at point 3, is equal to the total potential energy up here. So I can actually say, and we'll run through this, I'll either put it on La Lima or we'll run through it in class, but we can say that mgh is our potential energy here, which transfers to our kinetic energy here, which transfers to our work done by friction here. So we can say that potential energy at this point is equal to the work done by friction out here. So mgh, which we said was 1,960 joules, is how much work is done by friction here. And so the work done by friction is a force times the distance, right? So in order to figure out how far it goes, we just need to set 1,960 equal to the force times the distance. We can find the force because we have a mass and we have a coefficient of kinetic friction. We can find the force here, and then we'll just need to find the distance. But we'll do this one later. So putting what I just said into mathematical form, basically what we have here is that your final kinetic energy plus your final gravitational potential energy plus your final elastic potential energy is equal to what you had in the initial state, initial kinetic, initial gravitational potential, initial elastic, plus some change in all of this, which is the work done by other sources, right? Maybe the work done by friction, right? So this just says, are all of our energies in the final are equal to all of our initial energies, and then whatever work was done. This could be a positive work or a negative work. If we substitute, then if we say, we just let potential energy be gravitational potential and our elastic potential, then we'll just say this is a U, then we would get the final kinetic energy plus final potential energy is equal to initial kinetic plus initial potential plus the work done by everything else. All I did there is just put these together. Just say that all of our potential energies plus all of our kinetic energies are equal in the same, the final condition is equal to the initial condition plus some change in them, which is the work. This is really not anything different than the conservation of energy, but this is conservation of mechanical energy, right? In which we need to compensate for the forces of friction or those dissipative forces, and some sort of dissipative forces that don't allow us to convert directly between forms of mechanical energies. So basically this says that the difference in total mechanical energy is equal to the work done by other dissipative forces. We can rewrite this. I didn't do it here, but I could rewrite it and say, this is my total final energy, this is my total initial energy. TE final minus TE initial is equal to my work done, right? This can be positive or negative, depending on whether or not I'm putting work into it or I'm taking work out. If friction is working on it, it's probably negative. If I'm pushing on it, then it's positive. So just in summary, a conservative force is a force that allows this two-way conversion between kinetic and potential energies. So I can go from a kinetic energy, something moving, to a potential energy. Like if I were to throw something up, like throw a ball up, it has kinetic energy when it leaves your hand. If it goes up to the top, it turns into potential energy. So it has kinetic energy when it leaves your hand, potential energy, and it's all potential energy at the top because it stops moving, so there's no kinetic energy, and then it drops back down, turns back into kinetic energy again. So throwing a ball up, if I neglect any air drag, then gravity is a conservative force, right? It allows conversion between the kinetic and potential, and I don't lose anything. So the work of a conservative force is always reversible. I can always undo it and turn it back into the other form. A non-conservative force is one that dissipates the force so it can't be turned back into, or it can't be converted between kinetic and potential without any energy losses. So friction is the perfect example of this, or air drag. Really good examples of that, in which, I can't, if I push something along a box along a floor, then I can't get that energy back that was dissipated by friction, right? Because it's now in the form of heat in the floor. So, picture summary here. If I have, gravity is a conservative force, right? And if I have a conservative force, it doesn't really matter my path as something moves either. It's always going to be the same kind of total change in energy, right? If I have a runner starts here, runs straight up, then I have some change in potential energy. Here's here, right? Whatever this height is change in potential energy. But if the runner runs up over very hard here and then much easier on the way down, then the energy at the end is the same here, right? The change in potential energy is the same. Or if the runner starts out easy, runs down, then across, then back up, makes it hard at the end, then it's still the same total amount of work done, or the same energy at the end, because gravity is conservative. So conservative forces, gravity is independent of the path, or the work done is independent of the path. I think I said gravity. Gravity is a conservative force, and the work done is independent of the path if it is a conservative force. So once we have work and energy defined, power is actually a very simple definition after that, and it's just the rate at which work is done, or the rate at which energy is consumed, right? So average power is simply a change in work over a change in time. It's the rate at which work is done, right? Or instantaneous power would be the change in work over the time, but as the time gets really, really close to zero, so as it's closer and closer to zero, it's the instantaneous power. The SI units for power are in, watts are in joules, time is in seconds, so it's in joules per second, which is defined as a watt. So a watt is 1 joule per second. So take a look at your power bill. Your power bill isn't really a power bill at all, actually. It's a energy bill, because it doesn't make sense to charge someone for the rate at which they use their power. They're actually charging you for the energy. So the way they charge you is they say it's kilowatt hour. So kilo would be 1,000, so 1,000 watt, and then they put a hyphen times hour, right? So they're actually multiplying it by a time. So I take a joule per second times hours, or 3,600 seconds. Seconds would disappear, and I would have just joules, right? So power bill isn't actually a power bill at all. It's actually just an energy bill, because they charge you per kilowatt hour, right? So how long you've been using your power at that rate. So yeah, pretty straightforward anyways. Average power, or power, is just the rate at which work is done, or rate at which energy is done. So if we, somebody's climbing a skyscraper here, right? So somebody's climbing up the skyscraper, and they decide to take the stairs because they want to work out a little bit. Does it matter? They're going to use energy, right? They're going to obviously use some energy to get to the top. Are they going to use more energy or less energy, or the same energy, if they do this faster? If they go faster up here, are they using more energy, or are they less or the same? I'll give you guys a second to answer that. And you guys all said the same, right? It's going to be the same exact energy, because the change in height, the person starting out down here and they go up here, the change in potential energy is the same regardless of how long it takes her to get up there. The change in potential energy is exactly the same, right? So the energy consumed is the same regardless if it takes her a week or if it takes her 20 minutes to run up to the top, right? But the power would be different, right? If she does it faster, then it's over a smaller time interval, right? So the power would be greater. If she does it faster, she uses more power or exerts more power, but the energy that she uses is exactly the same. So here, hopefully that led you into this question, but let's do a practice question here. If work is done twice as quickly, then the power expended is what? You do it twice as fast. Twice as fast means half the time, right? So if you spend half the time doing it, write out the equation here. Put a 1/2 for time, and then figure out what the power is, and you should say twice as much power, right? If I did it in half the time, I did twice as much power. Or if I do it twice as quick, then the power is twice as much. Okay, one last thing to think about, and I'm going to leave it here without going through the entire derivation here, but let's say we're going to design a roller coaster that goes through a loop-the-loop, and we need to know how fast it's going to have to go through that loop in order for it to not fall. So I'm going to put this, we're going to do it in class, and also I'll put a solution to this on Lima, but we actually need to use some chapter 6 stuff here. So I want you guys to think about this for a little bit. Draw a free body diagram of the cart when it's at the very top of the loop. And you, in order for it to not fall, there must be a normal force, right? So we need to say that normal force cannot be equal to 0, okay? And then you'll have a weight in there, you'll have a normal force, and you'll have some acceleration, right? Which is equal to your radial acceleration, or v squared over r. And so put in an inequality, set that up, so solve for the normal force, and then find an inequality so the normal force is greater than or equal to 0. And tell me what the radial acceleration has to be. I do have the answers on the slide, but I'm not going to show them because I want you guys to try this, and I'll put the solutions for it on La Lima, and we'll also do it in class. But I'm going to leave this this chapter with that question, and then we'll do a class demonstration of how high we actually need some cart to drop from in order to make it through a loop-to-loop based off of energy analysis.